So now we're ready to do our sampling bowl problem. So again, it's believed that a sampling bowl in this Calvin's classroom has 20% red beads in it, that it is possible that someone has recently tampered with the bowl, replacing some of the red beads with white. As Calvin takes a sample of 100 beads from the bowl and 13 of them are red, does this provide evidence that the bowl has a lower percentage of red beads than it used to? I'm going to follow my steps. My first thing that I want to do is define my parameter. So P equals the true proportion of red beads in the bowl. Now I'm going to go ahead and do my hypothesis statements. My null hypothesis is that P equals 0.2. So 20% was what I believed to be true at the beginning of the problem. My alternate hypothesis is that P is less than 0.2, since I'm trying to show that there's a lower percentage of red beads than there used to be. Now I'm ready to move on to conditions. So my first condition is that I have a random or representative sample. It doesn't say random. I probably meant to put random, but I'm going to go ahead and assume that it's a random or representative sample. My second condition is the 10% rule, so I need to assume that my sample size, 100, is less than 10% of my entire population, which is all the red beads in the bowl. And I think that's safe to assume. My last condition is my success-failure condition, so NP and NQ need to be greater than or equal to 10. N is 100 and P is 0.2, since that's what we're assuming to be true. So 100 times 0.2 is 20, and that's greater than 10 for sure. NQ, 100 times 0.8, which is 80, also greater than or equal to 10. So that tells me that a normal model is appropriate for this distribution. Now I'm ready to move on to my calculations. My calculations are finding the probability of getting what we got in the sample, which is 13 out of 100, in this sampling distribution of all possible samples I could have picked. So I'm going to draw that out as a normal model. So I know, because of my conditions passing, that this distribution of all sample proportions is roughly normal. So now I'm going to find the mean and the standard deviation of that sampling distribution that I'm looking at. So same formulas as last unit with sampling distributions. Mu p hat equals p, which is 0.2. And standard deviation, or sigma p hat, equals square root of p 1 minus p over n. So let me go ahead and plug this in, and that comes out to 0.04. So I have a normal model with a mean of 0.2 and a standard deviation of 0.04. And again, I'm finding the probability of a sample proportion having 13 out of 100. So 13 out of 100, 13% is down here somewhere, and we're going to do that or less. So I'm finding a z-score. My observed value is 13 out of 100 minus my mean, which is 0.2, divided by my standard deviation, which is 0.04. And that comes out to negative 1.75 as my z-score. So now I'm going to look on a z-table or use normal CDF in my calculator to find that probability, which comes out to 0.0401. And we call that probability the p-value. So now we're ready to go ahead and make our conclusion. And our conclusion is going to be based on that probability that we just found. So let's talk about how to write a conclusion. Well, our conclusion is going to have to do with something we call the level of significance. The level of significance is what we're going to compare our p-value to decide how unlikely or likely it is. This level of significance can be any value. The most common ones that are used in general in statistics, 0.10, 0.05, and 0.01, so 10%, 5%, 1%, but 0.05 is probably the most common. So that means if our p-value, if our probability is less than that percent, then we're going to doubt that our assumption that our original hypothesis is true. Typically, if a statistician wants a test that requires stronger evidence, we would use a lower alpha value, because that would mean that it would take a really, really small probability to prove or to have evidence that something's changed. But typically this value is given to you, and if it's not, it's always okay to use 0.05. And that's what we're going to do on this problem. So once you know your level of significance and you know your p-value, we're going to compare our p-value to our level of significance. So remember, it can be any value, we're going to use 0.05. So if our p-value is less than or equal to our alpha, it looks like an A, but it really is a Greek letter, fish-looking thing. So if our p-value is less than our alpha, less than or equal to, then we say we reject the null hypothesis. So the silly little rhyme that I use to remember this sometimes, if p is low, reject the hoe. On the other hand, if our p-value is greater than our alpha, what we say is that we fail to reject the null hypothesis. So if that probability is really big, it means we don't really have evidence that the null hypothesis is different from what we thought. We're never, ever, ever, ever going to say that we accept the null hypothesis. This is because we are not actually doing a hypothesis test to prove whether the null hypothesis is true or not. That's not our goal. Our goal is to decide if there's evidence of an alternate hypothesis. So if we have a really high p-value, what that means is we don't have evidence that the null hypothesis isn't true, but we're never going to say that we accept the null hypothesis because we can't say for sure that it is true. So when we write our actual conclusion, since our p-value is less than or greater than alpha, whichever one it is, we're going to reject or fail to reject the null hypothesis. But then we have to go on from that and talk about what that means for our problem and answer the question that is asked. So we say that we have or lack sufficient evidence to suggest that our alternate hypothesis is true. If our p-value is less than alpha, we reject the null hypothesis. That means we have evidence that our alternate hypothesis is true. On the other hand, if our p-value is greater than alpha, we fail to reject the null hypothesis. That means we don't have evidence or we lack evidence that the alternate hypothesis is true. Remember to always put your alternate hypothesis in this sentence should be in words, in context of the actual problem you're doing. So let's go back to our problem and finish it up. Our p-value, remember, was 0.0401. We are not given an alpha, so I'm just going to go ahead and use alpha of 0.05. Okay, since my p-value is less than my alpha, we reject our null hypothesis. And that means that we have evidence that our alternate hypothesis is true, meaning we have evidence that less than 20% of the beads are red. And that's our conclusion. Last part, there's a part B to this problem that asks us to interpret the p-value. Now we're always going to write a conclusion to any time we do a hypothesis test. We don't need to be asked to do that. But on part B, you're asked to interpret the p-value, and that's not something you have to do every single time. We just need to do it when you're asked. So interpreting the p-value means explaining what our probability actually is on the normal model. So imagine, if you remember, our normal model looks something like this. Mean was 0.2, and we were finding the probability of getting a 13 out of 100, or 13% or less. And that p-value of 0.0401, we're going to try to interpret what it looks like on the normal model. It's kind of a hard thing to do, to put the words in the right places sometimes, so I kind of have a little fill-in-the-blank sort of explanation here, but I think it's going to make more sense if we go straight to our example. So that's what we're going to do. So I'm going to interpret that p-value, assuming that the null hypothesis is true, meaning assuming that 20% really is the true proportion. Our p-value is the probability of getting what we got in the sample, or more extreme. In this case, more extreme meaning less than, since that's what we tested for. So 0.0401, our p-value, is the probability of a random sample having 13 out of 100 red beads or less. And that's what we found on the normal model, so that is what we're trying to interpret. So that's it for this problem. There will be one other video that shows how to find those p-values and probabilities on the calculator.